Hi. So thanks for the invitation. I'm glad to have come all the way from Pavilion E over here to speak to you today. I want to talk to you about some things related to Heegard Floer homology, in particular when it vanishes. So some of this is joint work with different people, and some of it is independent. The thing about the torus links and algebraic links is what Maciej asked me to work on. So anyway, Nathan already told you a lot of what you need to know about L spaces. So they're spaces with reduced Heegard Floer homology vanishing. So the Heegard Floer homology splits over spin C structures, which you could view as an affine copy of H1. And so if you have an L space, it just means that in the hat Floer homology, you have exactly as many classes as there are classes in the first homology. Or if you're thinking about it in terms of reduced Floer homology, the reduced Floer homology vanishes. So examples are lens spaces or branch double covers of alternating knots, but there are lots of other examples too. And there's a conjecture of Boyer, Gordon, Watson, and Juhas and Nemeth that, well, so the first one, that M is not an L space if and only if its fundamental group bits a left invariant order. So Juhas wrote down the conjecture that is sort of implicit in the first one, that paper that Boyer, Gordon, and Watson wrote, that M is not an L space if and only if it has a co-oriented top foliation. I should point out this is not a co-oriented top foliation, but it's very pretty, so I thought. And Nemeth conjectured, and in fact recently proved, that M is, so if M links a normal complex surface singularity, then it links a non-rational singularity if and only if M is not an L space. So Nathan's talk was more about this sort of canonical hard case, which is when you have a hyperbolic manifold. But I'm trying to view the problem, at least in this talk, from the standpoint of gluing things together, sort of seeing if when I stick different pieces of manifolds together, whether I still get an L space or if I don't, or whether I still get a top foliation or I don't. So if the thing I glued two manifolds along is a two-sphere, then I just have a connected sum. And so the hat Heegard Floer homology just tensors, since I've got a rational homology sphere here. The fundamental group just is a free product. I don't have any top foliations on the connected sum. And I'm an L space on the left if and only if I'm an L space on both the modern side on the right. And the same thing is true for left orderability. And though I don't have the same statement for top foliations, I do for tight contact structures. So what this really tells us is that we don't learn any new information from studying manifolds which are not irreducible. So we might as well focus on prime manifolds. Okay, so what if we're gluing along something that's a higher genus surface? Well, then M is Haken, and so we have a sutured Floer homology and a top sutured decomposition of, and so we can kind of study both the Heegard Floer homology and top foliation simultaneously from that respect. But from a left ordering point of view, that's harder because surface subgroups are hard to get at, and there's not as much done there. But if you have an essential torus, then, well, and M is toroidal. And that's the case that I'm going to focus on more. There are more tools that are sort of available to hand to work with. So, for example, if you have a graph manifold, which is where all of the components in your JSJ decomposition are ciphered fibered, then Boyer and Clay were able to show that your graph manifold has co-oriented top foliations if and only if the fundamental group is left orderable. And then my collaborators, Hinselman and Jake and Liam and I, were able to show that a graph manifold M is not an L space if and only if it has co-oriented top foliations. And so that gives the Boyer-Gordon-Watson and Juhasz conjecture for graph manifolds, if you combine those two results. And then Nemethy was able to use that result to prove the final part of his conjecture about lengths of rational surface singularities. So the next thing you could ask about is what about knots that are in satellites, right? Like if I have something that's hyperbolic that's glued to a graph manifold or to a cyclotomic manifold. So I'm going to study Dane surgeries on satellites of knots. And let's warm up with a little bit of nil surgery first. So we're all a bit jet lagged at this time of day. So the even easier than Dane surgery is what if you cut out a manifold with a two-sphere boundary? So you start with a three manifold you don't like. You cut out a manifold with two-sphere boundary. You replace it with another manifold with the same boundary, and you get a manifold you do like. And you have to ask that this is induced by an elementary cobordism. In this case, it would be just a trivial cobordism, so you probably shouldn't even put genus in there. But unfortunately, the easiest initiatives to describe aren't always the most effective ones to implement. So this might not be the solution to our problem at the moment. But let's see. So we do have L-space intervals when we're talking about Dane surgery. So Nathan already drew a picture over here of when you close you attach some two-handle along a meridian to make a Dane filling of your manifold with torus boundary. And it turns out that the space of slopes which give you L-space Dane fillings takes the form of an interval, or it can be empty or it can be a point. So it's either a closed interval, by which I mean it's the intersection with the sort of rational looking projective line with a closed interval in the real projective line, or it can be the complement of the rational longitude, or it can be an isolated L-space Dane filling, or it can be empty. And I use that notation to mean interior. So we were able to prove the gluing theorem about when the union of two three manifolds gives an L space in terms of the slopes, space of L space Dane fillings of the individual manifolds. So who's the audio video person? I'm done with the slide part for now. So if we've got a single torus boundary, right? We've got our L space interval, which is the space of L space Dane fillings. And similarly, you could write down the space of left orderable fillings, so such that y alpha is a left orderable. And for this, due to a kind of quirky thing about what's proven for top foliations, here I would say y admits a coriented top foliation f such that f restricts on the boundary to a product foliation of slope alpha. And this is contained in the set of foliation slopes defined in terms of Dane fillings if you were doing it in the other way. And in fact, these two are equal if you're talking about graph manifolds. But for an arbitrary three manifold with boundary, the reverse conclusion is not proven. So it's probably true, but it's not known. So this doesn't go up, does it? Okay, I can still go here. So we know some things about gluing for each of these, right? We've got the if and only if statement. Here, so let's see. So if the closure of this is non-empty, then, and here I should say, where I've got a gluing map on the, on the boundaries. This is known to be true if the yi's are Floer simple. That was proved by Jake and me, or if they're of so-called loop type, which was proven by Hanselman and Watson, and then Hanselman and Watson and Jake are working on showing it just in the general case. But we already have sort of partial results in these other cases, right? So if these are slopes are non-empty, then that implies that, sorry, one, and again I've got this. Then and this is a result of Adam, Ty, and Liam working on sort of making an observation about an amalgamation result of blue dolphin glass. And then also, if we've got.
It's wrong atom. You want Adam's flare.
What?
You want Adam's flare.
Oh, do I have the wrong atom?
I think so.
Oops, I did. Okay. Oh, I totally did. I was looking at the last one. Okay, sorry, wrong atom. Actually, that atom makes more sense for this topic. Okay. Thank you. All right. So, where's it? Oh. And then we've got this. I mean, it's kind of funny that it's much harder to glue something along a matching slope for in Heegard-Floer homology than it is in these other two cases. I mean, these two things are relatively easy to glue together, whereas this is kind of taking some pretty new machinery. So. I mean, and you would sort of want to have the converse statements of these be true too, but you can't hope for the converse statements to be true because these are sort of only a weak description of what the slope behavior of what the gluing behavior for left orderability and foliations is. Yeah. Actually, did I? I don't think it's, yes. Thank you. So there are other ways to glue foliations together besides along a product foliation. And in particular, if you look at the closure of these sets, you tend to get a foliation which restricts on the boundary to a top foliation that has non-trivial holonomy. And sometimes you can glue those together. And in fact, if you're in a graph manifold, you always can find two top foliations with non-trivial holonomy at these endpoints at which you can glue together. And the same sort of an analogous kind of behavior happens for left orders. But you can still get a lot of gluing just from the sort of the simplest versions of these clones. So anyway, that's partly a motivation for some of what I was going to talk about. Oh, and I guess one more thing. So there's also a theorem by Jake and me that, well, Nathan already mentioned this, that the so the L-space interval of y is determined by the Turayev torsion of y. And two L-space fillings. Of course, this is assuming you have two L-space fillings. Otherwise, if you have only one or none, and so you have to know what that one guy is, or that you don't have any. Okay, so in some respect, that tells us a lot about what's happening for a single torus boundary case. And so people are starting to wonder about what happens when you have multiple boundary components. So let's see. So what if we have links? So Eugene Gorski and Andras Nemeti have started looking at this question initially for algebraic links, but also in other cases using the link Floer homology for two-component links in S3. But one of the earliest results in this is they showed that algebraic links are L-space links. By which they mean sort of in analog to what we call an L space not an S3, where if you have a sufficiently large integer surgery, you get an L space. For an L space link, if you have a link in S3 and there's a sufficiently large integer, finite integer in both slopes that gives you an L space, then you're an L space link. So then there was, and Liu showed that for a two-component link in S3, the region of L space Bain surgeries is determined by the multivariable Alexander polynomial. Okay, so in this case, I'm going to talk about building links by a satellite operation, where it's sort of analogous to cabling, except instead of taking a cable by a torus knot, I'm taking a cable by a torus link. So, you take the knot complement, you glue in a torus link along the boundary of the neighborhood, and then you've got a link complement. So this is something that I discovered Gorski and Hama already looked at. So a torus link satellite of an L space knot is an L space link if 2g minus k1 is less than q over p, which should remind you, if you're familiar with it, of the result about cabling by Hedden and Hom. So if I have a positive L space knot, and by positive I just mean that I've oriented the knot so that my big surgeries are in the positive slope direction instead of the negative slope direction. Non-trivial. Then, and let's say that y is the exterior, then the L space interval for y is given by just infinity if this is, now, first of all, let me just say, for k, so let me write here, Q. Where y, np, nq is the exterior of and here they have n equals 1. So L space interval for y is always going to be 2gk minus 1 to infinity. This is an earlier result of Peter and Zoltan, but you could also show it using the Turayev torsion computation that we have here. So anyway, if this is greater than Q over P, and P is not equal to 1, or it is, let's say, NPQ if this is, and or P is equal to 1. And here, NPQ is the new number you would compute from the new genus of the table. So it's PQ minus Q minus P. Or so anyway, using, oh, I didn't erase this one. Using this Turayev torsion method, I was able to compute what the L space interval for a general ciphered fibered space looks like, and it sort of gives a direct computation of an older result that combines work of the Eisenbud-Hirsch-Neumann and Jenkins-Neumann-Naimi and Liska-Medic and Liska Stipschitz to show which ciphered fibered spaces are L spaces. And then using this gluing method, you can extend this L space interval description for ciphered fibered spaces to an analogous formula for graph manifolds. And this turns out to be a very powerful formula for computing things about cables or satellites that involve gluing on torus links. So that's sort of the method that I used. Okay, so So let's see, I've already told you what the Y, NP, NQ is the exterior, so that K is a positive L space not. Possibly trivial. And I've got NT greater than 0, and so I have L of Y now, this is a lot of notation, kind of, but I'll talk more about what this is. So this is a particular action which acts on the space of slopes. And it comes from, if you're familiar with working with ciphered fibered spaces, you have ciphered data. You write something like this. I've got some ciphered fibered space over S2. I've got ciphered slopes like this. Well, this is only defined up to an overall addition of integers here, which sum to 0, right? So I can also say so I have this lattice, lambda, sitting inside my space of slopes, which is just this, these L, and maybe this would be better. So this is in the N. So that these integers sum to 0. And so that's lambda in the ciphered fibered basis, but I'm working right now in the link exterior basis in S3. So you have to change basis before you think about how this acts. And it acts in a slightly different or more complicated way once you've changed basis. So anyway, if greater than T, then so that's first case. And then second case. Let me write this down and then I'll talk more about what this means. So I've got okay. So, this may look horrible, but it's actually precisely the analog of this Hedden-Hom result. So, what we've got here is, where should I write this? Over here.
Sir,
Mhm.
the board down so we can see.
Oh, sorry. So if you look at the result for just a single component where you've got a cable, it looks like this, right? I've got, here's PQ, this is my reducible filling, here's infinity, and here's NPQ. So I've got this interval here, L spaces, and I've got this interval here, L spaces, all of which are irreducible, and then I've got this one reducible filling here in the middle. Okay, so if I look here, this gives me my that part. This part is a little funnier looking, but but if you think about it, that's the same thing as this, right? If I start out with this entire interval and then I take out this chunk, then I'm left with this. And then this part here, so these are the reducible fillings, which are, well, not a connected sum with S1 cross S2. So in this case, when there's a single component, there are no, all of the reducible fillings just give you an L space. So you don't have to worry about this spot. But once you have more components, you start to need to worry about having reducible fillings which have an S1 cross S2 in there. So this these three spaces, this lambda, R, and Z, have their simplest description in terms of the ciphered fiber basis, right? So I already wrote for you what lambda looks like in the ciphered fiber basis. And here, for my ciphered fiber basis, I use slopes. It's a reverse-oriented basis, so I use slopes that look just like ciphered slopes. So if I have, so I've got this change of basis. So this is ciphered fibers, and this is the link exterior in S3 basis, then it looks like Okay, so if you think about when you get reducible slopes in a ciphered fibered space, my R is going to be right, so I get a reducible slope from filling in the infinity ciphered fibered slope when I'm working in a ciphered fibered basis. So that translates to just PQ in this change of basis. So the reducible slopes come at these hyperplanes in my space of slopes, and then the ones that have that are connected some with S1 cross S2. Those are codimension 1 subset of those that have two guys that are equal to PQ. So if you want to draw this for a two-component link, looks like this. Let's see. So if this is PQ, then I've got this region here, and then I've got this region here. But then then I've got to take out, this is PQ. And so this gives me this space here and this space here, and then for the reducibles, that's given by line here and this line here, but then I have to delete this point here in the middle, so that's Z, that's my exceptional reducible set, and then this is R. And then, you know, if you have higher dimensions, you have the same picture. So this lambda action is completely irrelevant if all you care about is the manifold you're getting rather than the slopes, right? Because the this lambda action, which is acting on the ciphered fibered space that I've glued onto my my knot exterior, does not change the homeomorphism class of the Dane filling that I get at the end. So if I just care about classifying L space free manifolds that result from Dane surgery on these links, then this is all I need to know. But if I want to know about the actual space of slopes, I have to also take into account this lambda action. Now this lambda action is lambda is 0 if I have just a cable, if I have just one component. So it doesn't become non-trivial until you have more than one component. So here, and well, in any case, you get the nice thing about lambda is that it's pretty well controlled. So I get this kind of this neighborhood here. PQ minus 1 and PQ plus 1 of the of the reducible locus. So there's this radius 1 neighborhood of the reducible locus, and all of the extra orbits that I add in from lambda land in this neighborhood. So I get some extra stuff here, which looks kind of, let's see, I don't know how to draw it very well. It looks sort of increasingly, also it would be sort of filled in here, and then it gets very complicated right inside this box. And it's like filled in here, and it's very complicated here, and likewise. Yeah. So, sorry, that's kind of vague looking, but I mean, it's just determined by taking this and acting on it with lambda. Although that's not the most efficient way to do it. I mean, the most efficient way to describe this space is in terms of the ciphered fibered basis. In fact, it has a much nicer description in terms of the ciphered fibered basis. It's just, we're used to thinking of things in terms of the not exterior basis. And so that's part of why it looks a little bit funny as you get closer to this region. Okay, so what should I say next?
Sorry, so in the theorem you apply the transformation only to R and Z. We have this two new chunks in part 2.
I'm sorry? Okay. All right. So yeah, actually, maybe let me just briefly describe in the ciphered fibered basis what this looks like. So this tells you also what happened. Oh, I wanted to say one more thing. So one thing that's kind of neat is that there's a different behavior at p equals 1 for whether you have whether your slope is whether n is greater than q over p or less than q over p. So in the cabling result, it didn't matter. There's only one behavior for p equals 1, and that's just that you get your original knot back, right? If you take the p equals 1 cable of a knot, you just get your knot back. Because you're just changing the framing and changing the winding number of this one guy when there's nothing to wind around doesn't do anything. But when you're changing the winding number of multiple components, it actually does do something. And so your cables, your satellite links when p equal 1 have a qualitatively different behavior depending on whether n is greater than q over p or less than q over p. So if it's greater than q over p, then the only L space fillings you get are the original surgeries on your knot. But if it's in this case, then you get sort of a great big family of other guys too. All right. So yeah, so in the ciphered fibered basis, remember I've got slopes y1 and y2, which look like sort of yi looks like beta I over alpha I if I'm looking at the well, the ciphered fibered space that I'm gluing on to make my cable. So, and then I have something there which looks like this, where and then I'd have a gluing map, which is also determined by the data of P and Q. for some ciphered fiber space, say, excludes monadic stereo to make. So in this basis, I've got this positive region here, so the L plus, say, looks like this for, let's see. So that's like this sort of, wait. Oh, it's like this staircasey thing. I might not have lined it up correctly with the axis. Yeah, I probably should shift the axis over as well. But anyway, and then the L minus thing is yi less than or equal to 0, almost, except that it's let's see, what did I do? So it's 0 is less than or equal to some guy. Okay, so let's see, y minus, where y minus is minus 1 over and this is if is equal to 0, and this is otherwise. So I've got this little chunk that I take out that corresponds to the chunk that I take out here. So when I have my negative region, it looks sort of like a staircase like this, but I have this little corner that gets missing. Right? And then I've also got my reducible region out here at infinity. And yeah, so that's basically what it looks like. So I wanted to talk briefly about two more things. One is what happens when I do this iteratively, so that I get an algebraic link satellite of something. And then what this says about the Boyer-Gordon-Watson conjecture. So. So the full description of what happens for the algebraic link is a little bit technical. So I want to just tell you sort of the simplest things about it that I can tell you. In particular, sort of a primary region that's contained by it. So let me get the page. Yeah. Okay. So this region, it comes sort of in strata, which describe how many times these two spaces kind of stay separated, whether I end up having an L space interval with the endpoints getting reversed or jump down to a new graph manifold. So if that doesn't happen, then I say I'm in the monotonic stratum, and that's sort of the biggest piece. So now I've got a graph instead of just this cabling data. So here that and the vertices correspond to the different satelliting operations, the different cyclic hybrid spaces. Hold on. So I've got a separate lambda for each guy, and then I've got my L min and my L space reducibles and my negative component, my positive component. And then here I'm contained in the same thing, but with maximum versions of these. So the interesting thing is that there's sort of a big chunk that looks like a product kind of in the middle. So that there's a big part of this L space region that's kind of independent of what's happening in the other cyclic hybrid spaces. So L min where that's the number of components that I can stain fill coming in that vertex. And then L max it's so it's the same thing. So this union some extra piece that I get if p equals 1, which I'm not going to write down right now. And then for the negative components, you get a piece which looks basically like the negative component here when you have a leaf, when you're at the edge of your graph. And if you're not a leaf, then the negative component almost vanishes. It lands inside this neighborhood that the lambda action goes in. So there's something there, but it gets kind of it's not very big. So maybe I should say it's like torus-link for leaves and small otherwise. Okay. Now I motivated this thing at the beginning with the Boyer-Gordon-Watson conjecture, and I haven't really come back to that yet. So I wanted to talk a little bit about this now. So since I can do this kind of weak gluing construction, I can still learn some things about what happens if I start out with an L space knot that satisfies the Boyer-Gordon-Watson conjecture, for example. So So suppose with those definitions that my space of product foliation, so my space of top foliations descending to product foliations is the same as the space of non-L space slopes for y the exterior of some L space knot. So if is greater than q over p, then So, all right. So if I'm in a situation where I just get these, oh, and let me also say, and this is for p greater than 1. So if I'm in the situation where the only surgery I get is that's an L space is S3, then from the standpoint of L spaces, that's really boring. But from the standpoint of non-L spaces, it's sort of the most interesting case because it means everything that every surgery I get has non-trivial Heegaard floor homology. So, and in this case, all of those spaces with non-trivial Heegaard floor homology have top foliations except for the reducible ones. So. Yeah, that's sense. Contains. Here I've got, so again, NL minus C minus this one region here, which is okay. So here, there's this little slice right here. For which the foliation regions or the non-L space regions or whatever you want to call it overlap right exactly at the endpoint. So I've got the ciphered fibered manifold that I'm. So this is if this is the non-L space region, say of my ciphered fibered space that I'm gluing to the knot, and this is the non-L space region for the original knot exterior, then they overlap at this one point here, and so that means I don't get an L space. But I do get, but I also don't get a foliation the stupid way by gluing product foliations because I have non-trivial holonomy when I restrict to the boundary here. And so I would have to know that I can find two foliations of matching non-trivial holonomy to glue together at that point. And for graph manifolds, you can always do this. That's what Boyer and Clay showed. But for arbitrary manifolds, we don't know how to do that. And then this whole story goes through again for left orders, because we have this sort of stupid gluing rule again for left orders, except here I don't get the an equal sign. So for left orders, I would just get a that it contains this set, right? Because you get a little more information about foliations from the fact that left L spaces exclude foliations, whereas you don't have this exclusion principle for left orders. Okay, so that's all I wanted to say, I guess. Yeah?
So, for a general, like, link in S3, say, I mean, what are the restrictions, if any, on the set of these L space fillings? I mean, like in your example, it seems like they're kind of like their boundary is some finite number of polyhedron or something, right? Kind of by lines in the picture.
Yeah.
Is it known they sort of have some, description as like a union of convex, finite union of convex polytopes, or?
Well, so it's interesting. I mean, for these spaces, this result gives you the impression that everything's kind of deterministic. And that's partly because I didn't draw any samples from the p equals 1 case. And in that case, the p equals 1 case for, say, a torus-link. It's even deterministic here for a satellite. But if you have a p equals 1 torus-link, and you do surgeries on that, you can get any ciphered fibered space you want through that mechanism. And the L space region for ciphered fibered spaces is chaotic. It's so if you look, it's sort of piecewise constant if you fix all components but one. But then, if you start moving more, changing more slopes, the dependence of the boundary points depends chaotically in a dynamical way on the way you change the slopes. And so in general, so cabling has a very special map that coincides just particularly with the cipher data in such a way that most of the chaotic behavior cancels out so that you can actually deterministically solve these formula and get answers. But for things that aren't cables, there's no reason for this chaotic behavior to cancel out. And so, you still have, because of the L space interval result, it's always the case that if you fix, if you look at some smaller subset where you've fixed n minus 1 of the components, then you'll get an interval. But in terms of the dependence of several variables at a time, it'll be chaotic in general. Yeah.
There's no more questions for Sarah.
Oh,
I'm so sorry. Ken, go ahead.
So say you have a two-component link whose set of L space slopes looks like the set of L space slopes of a two-component cable.
Uh-huh.
Is
We're
there?
about like a cabling conjecture for links or something?
Well,
Or
I mean, could you then say, well, actually, it's got to have this essential annulus and therefore also be a two-component cable? I mean, it seems somehow that annulus is causing a set of slopes to have a special structure.
yeah, I mean, I feel like going backwards to that statement would be equivalent to proving the cabling conjecture. I mean, I don't know for sure, but I do think that having more components and seeing this reducible set show up in a larger way brings a little more insight into where this reducible component comes from when we do have cables.
Well, I mean, I'm not saying necessarily that you have something that's reducible. I'm just saying slopes are or are not L spaces.
Oh,
Just the set of slopes which are, set of pairs of slopes which are L space slopes.
so you mean if you get a set where you have everything except for the
Yeah, but it's just like set-wise. It's
yeah. So so there's a characterization of and anytime I've got an L space interval that looks like this minus the rational longitude, then I've got a genus zero space. So it looks like like some kind of knot complement in a connected sum of S1 cross S2 plus something.
But that's when you have just one boundary component.
That's when you have just one boundary component. But if I have multiple boundary components, then I don't know. I guess then that's true one component at a time, and then you'd have to work out whatever the analogous statement would be. Any more questions?
Let's thank Sarah for a great talk.